give you the area of the sector of the circle, all right? The area of just the sector of the circle. Don't worry about the slivers yet. Let's just get the sector.
Yeah, it's polar.
Do you use R?
Which R represents the circle? You've got two R's.
Sine 2 theta.
No. R equals 2.
Okay.
You win one, you lose one.
Oh, R equals,
Yeah.
Are you like a pizza slice thing?
Then you just get like the whole thing. But then pass one half.
I forgot it.
Oh, then you
All right.
2 times.
Okay, so the sector of the circle, you all got 1/2 integral from what to what?
Pi over 12.
Pi 12s to 5 pi 12s of radius squared, right? 2 squared d theta? Good. Everyone comfortable with that?
Yeah.
All right, here comes the challenge. You can work together on this. I want you to figure out what limits to use, what radius to use to get the area of a sliver. You're going to want to put a 2 in front of it because we're going to double these, right? And then of course you still have your half, so they're going to cancel out. But anyway, so I want you to figure out area of a sliver.
From 0 to pi. Did you say 0?
So the red is the line.
Initial angle of the sliver and ending angle of the sliver. Beginning angle of the sliver, ending angle of the sliver.
And then it would just be 0. Yeah.
Wait, I think I got it. I don't mean I want to say that basically from like kind of stuff like washer, something of a bomb, something.
Why'd you say
So we got two of them, so we multiply by 2. And then from 0 to yeah.
Alright, so, we gotta move on. So, what is the beginning angle of the sliver, and is there a way you could figure it out analytically if you weren't sure?
Yeah.
What's the radius when the sliver starts?
0.
0. So you could set your Rho's function equal to 0 and solve, and you actually end up with an angle of 0.
I called it.
Right? So our beginning angle of our sliver is 0, and then we already figured out the final angle. What's the ending angle? Pi over 12, right? So the area of the sliver is the integral, 1/2 the integral from 0 to pi 12ths of this r squared. All right? Beginning angle for what you want to ending angle for what you want. Okay, the angles don't have to bound the picture. They just have to be the beginning and the ending. Okay?
Wait. Oh, what? Sorry, what?
That's
So the
okay.
angles.
The angles are not the actual, like, see this sliver? Y equals 0, or like theta equals 0, or whatever, is not a boundary, physical boundary of the region, but it's the starting angle of that region,
Oh.
right? And then the ending angle of that region is pi over 12.
Okay.
All right, does that kind of make sense?
Oh, and it's different because you use the equation of
Of the petal and not the circle, yeah?
Yeah, that sounds very
Okay, so. Oh, that's a lot of words. Okay, so anyway. Alright, so when you set up, this is your final setup. So, you have 4 times your sector of your circle, 1/2 times 2 squared, pi 12 5 pi 12, plus 2 slivers, right? So 1/2 0 to pi 12 of 4 sine 2 theta quantity squared.
No.
Alright, without doing the integral, because don't worry, I've got another one for you to do. Without doing the integral, this is your answer if you guys want to try to integrate it on your own. It's just another, this is an easy integral, and then this is just another power reduction, right? Be careful when you do a power reduction, since this one would be a sine squared 2 theta, your answer would be a 1 minus cosine 4 theta, right? Because you had double the angle. Okay. All right. Okay, last one. We're gonna find the area of the inner loop of r equals 4 minus 6 sine theta. Okay, all right. Now, yes, very good. Okay, I actually am gonna go ahead and give you the graph because we only have 5 minutes.
Yeah.
So,
Oh my gosh.
okay, this is what the whole graph looks like. There's like an outer loop and an inner loop, right?
Why?
Okay.
Kill me, Miss Pratt.
Alright.
Kill me.
Whoa.
Okay, that's the middle bill.
Alright,
Why?
now, we're finding the area of this guy right here. Notice, what is the radius for the beginning and ending of this region? It's 0, right? So you should be able to just set your r equal to 0 to find your starting and ending angles. Go ahead and do that. Take a second. Find the starting and ending angles by setting that radius equal to 0.
Do you get sine?
No calculators.
And we
You don't
have,
have to figure out the actual angle, you can leave it in terms of arc sine.
Okay, good.
do we have a calculator on the Captain Science test?
It's 50-50.
Wait, so it's not combined?
It's half calculator, half no calculator. I don't know what's on mine.
No, are the tests combined?
Wait, what? That's
Or as in like, are all the sheets on one side, like?
No, you will get, I think the calculator portion, you turn it in, and then you get the no calc or vice versa. All right, now, hey, so your angles. Now, there are 2 angles between 0 to 2 pi where the sine is 2/3, right? There are 2 angles. Do we know what they are?
No.
Okay, so here's what we have. We have an integral from arc sine 2/3 to arc sine 2/3. That's probably not going to give us an accurate area, right? Because the answer would always be
Why?
0. Okay, so how could we, yes, Cole?
I was joking around.
Okay, so Cole is like super on fire today, all right? I don't know if you guys heard that or not. He said, well, gosh, instead of going arc sine 2/3 to all the way to arc sine 2/3, this is where symmetry is our friend. Could we go from arc sine 2/3 to pi halves? Now I know pi halves is up here, but if you look, the radius at pi halves is actually -2. So arc sine 2/3 to pi halves, could we do that and double it?
Yeah.
Yes, we could, right?
Yeah, Cole.
Okay, so I want you guys to see if you can at least do the setup of this integral and kind of start evaluating it. Yes, I see.
That's fun.
Oh
The
my
good
god.
news is we do this again a bunch tomorrow, so you'll get more, I know, happy.
That's very good
So you'll get
news.
more practice.
Why is that good?
You can multiply that.
Because you need more, something tells me you need more practice. Maybe not, but only if you don't have the graph, how do you That would be tricky. That's why I graphed it. I didn't even know what the inner circle was until I graphed it.
Wait, so we have to grab it? What do you mean, sorry, good?
I almost always graph. I'm a very visual person. You could. Yep. But I think it's easier to just go to pi halves. But yeah. Yep. Okay. So your setup. Uh-oh, there's a long explanation. Okay, so you can read that on your own. All right. So there's your setup. So we're going to double 1/2 integral from arc sine 2/3 to pi halves of 4 minus 6 sine theta squared. When you square this, of course, you have to square the whole quantity, right? So you get this lovely thing. I can integrate this. I can integrate this. how do I integrate sine squared? What do I have to do? Power reduction. Is it gonna be a 1/2 times 1 plus or 1 minus? Minus, right, okay. So, yeah, because James is bad. Sine subtract, okay, whatever. Alright, so, alright, so we plug in, we do our power reduction, then we integrate, plug in. Now, I can do cosine of arcsine 2/3 just fine, but you can't do the sine of 2 arcsine 2/3. You can't have a number in between the function and the inverse function. So you have to use a double angle identity for sine, so that it's 2 sine theta cosine theta, so you get 2 sine arcsine 2/3 times 2 cosine arcsine 2/3.
Oh, my
Right?
goodness.
Oh,
Right? Okay.
As everybody knows.
Alright, I know, we're wrapping up. So, I'm gonna turn off the recorder, but I have something else to tell you before we wrap it up for good.